will have heard Neil talk last year and know what a very good and fun, dynamic speaker he is. And we're very lucky that he could come. Of course, he is married to Dr. Cheryl Peach, who organizes these lectures, and maybe she was able to twist his arm. Neil is a professor in the Geological Research Division at Scripps. And he came to Scripps in 2000 from what we call that other place on the East Coast. In other words, Woods Hole. Now, Neil's primary interest is in the study of plate tectonics and sedimentation on the margins of continents. And today he's going to share some of his very recent work that he's done on the faulting and sedimentary record in the waters just offshore here. And I had the very good fortune to go out with Neil and his colleague Jeff Babcock and some scientists from Woods Hole, well, only just a few days ago. And it was very exciting to be able to watch the expertise and enthusiasm of these scientists as they deployed their instruments off the boat and were actually recording with sonar and cameras the bottom of the ocean that had never been explored in that very spot before in that way. It was like suddenly being able to go to a spaceship and look at Mars. This is something new and exciting. And so Neil is going to share some of that excitement with us today as he talks about the geology in our backyard. Neil.
As Nigella pointed out, my interest is in what shapes landscapes and seascapes, the processes that shape the surface of the earth that we see, that we walk on, and the surface beneath the water. Okay? So today, some of you, I gave a lecture about a year ago, and I'm going to introduce some of the concepts again, but I'm going to present some of the data that we've collected since that last talk that shed some light on the processes that have shaped La Jolla. And we've used a variety of instruments, and one of the breakthroughs I think our group has done is that we put this data into a visualization cube or a volume so that we can bring disparate data together, co-register it, and look at it in a way that you can digest the information and start to make realization of the processes that are operative. So here, one of my main interests is trying to understand landscape and seascape evolution and the processes that form them. What are the dominant and what are the subordinate processes? You'll hear this a few times in my talk. It's a phrase that my group has coined. But the surface of the earth that you look at today, whether it be exposed subaerially or beneath the ocean, tomorrow that becomes stratigraphy. And if I'm ever going to be able to read the stratigraphy and try to understand what happened in the past, I have to be an accurate reader of the morphology that records the present. The present allows us a lot of opportunities such as dating things, measuring stream inputs, tectonic uprates, deformation. So if I can understand how the landscape records processes I can measure and see today, then I can infer better what's happening in the past when I see these shapes or these features. Also, I think it's important for scientists now to look more towards guiding people that make decisions. We have to be tied into people that have the responsibility to society to understand some of the hazards. We'll never be able to predict some of the things I'll talk to you about today, like tsunamis, but we'll be able to better understand places that are more susceptible, and we might make planning and strategy to mitigate the effects of these hazards. Before I go on, I'd like to acknowledge my group here. I'm very happy with them, which is not shown in this picture. I'd like to start off, J.P. Walsh, the second in from the left, is a postdoc in my group doing some really great science and has contributed some of what I'm going to talk to you about today. Jenna Hill in the left, as a graduate student doing PhD work. She's working on the U.S. East Coast. This picture is in Dutch Harbor, Alaska. Part of her thesis will be in Alaska, looking at how sea level rise affected communication between the Pacific and Arctic Oceans and implications for climate. Jen Haas in the middle is a master's student that will be working on looking at some of the sands with depth off of La Jolla, and will be involved in this project. Christy Lindemann works in my lab. She was an undergrad here at UCSD. Wilson Wong, we call him Tsunami Man, and I'll be presenting some of his work that he's done with me on tsunami possibilities in the La Jolla area. Kurt Schwer, who's not in this picture, is also put together some of the 3D renderings that we're going to see, and is a very talented graduate student with Lisa Tokes and myself. So this group is really an exciting group to work with. Also, we work a lot with Jeff Babcock and Graham Kent, who are involved in some of the data I'm going to show today. So basically, I'm going to backstep a little bit and talk about the theory of plate tectonics, how this imparts a signature into the landscapes and seascapes, and talk to you about this theory. Okay, so here, I would tell you that when we look at landscapes and seascapes, they record this interplay of processes: tectonic deformation, erosion, sedimentation, climate, such as weathering, rainfall, wave base, okay? So it's an interplay of many processes, and trying to tease out which process is most important is very difficult. It's like reading a book with many of the pages ripped out, okay? You have to put together the story from an incomplete record. And we're always trying to find the best way to image this record, so that with technology we can at least image the pages in the book that still exist. Okay, so the stratigraphy and morphology. So today's morphology are the surfaces you look at. Some get buried and preserved and make it into the geologic record. Why do these layers actually make it into the record, and which ones do? We're still working on. Okay, when I was in school, it was always thought the big storm events or the big landslides, these were the things that made it into the record. Well, it's not that simple. So what actually passes from what we see today to what's the record for tomorrow is not an easy filter or transmission signal. Okay, so we're trying to look at these records because they're tape recorders of Earth history and deformation. And as I said before, it really is trying to understand the processes that shape the present that will allow us to look into the past and understand maybe some of the processes that were operative then. Theory of plate tectonics. Basically, it's a theory that the Earth is comprised of plates, roughly about 12. These plates are strong members. They deform at their edges. They're largely defined by earthquakes, okay? These rigid plates interact in three major type of boundaries, okay? And these boundaries are divergent, ridges and rifts, okay? Convergent, we have subduction, trenches, mountain building, so where the plates come together. And we have translational, where the plates move by one another, okay? The theory of plate tectonics is a very exciting theory, and there's a lot of complications. It sounds very simple when I present it here, but these plate boundaries are nothing but simple when you start to look at them. Let's just simply go through this. The Earth isn't expanding, so when we create new plates at the ridge crest here, what happens is this plate moves along like a conveyor belt, the oceanic lithosphere, and it's recycled at convergence zones and is subducted back down into the Earth. And as this process happens, what we do is we get melting occurring, and this melting then makes it back to the surface in these volcanic arcs. So here, this conveyor belt allows us to regenerate the seafloors. The seafloors are younger. The continents are the older part of the plate, some ranging back to billions of years old, the interior cratons. And these continents are mostly the recycled material and collision material that's scraped off because it's more buoyant and doesn't get recycled. So here we're looking at a divergent plate boundary where the plate is being generated. It moves on this conveyor belt, subducted, recycled. Well, this doesn't take into account the translational boundary I talked to you about. So here in California, we used to have a convergent plate boundary with subduction going on. What happened was the Pacific plate was spreading, and here the ridge crest, where it was spreading, was subducted beneath the North American plate. And it first started about LA, Los Angeles. And I said to myself I'd make no jokes about the recall today. So anyhow, so here, as the ridge crest is subducted, the plate boundary here, going from convergent, where we're recycling the oceanic lithosphere back into the Earth, and here where we're generating and spreading it, the boundary changes to a translational type boundary, and this boundary migrated both north and south. And the first subduction of this happened somewhere about 30 million years ago. And so you can see that this is evolving into the San Andreas Fault, and down here we have small spreading. We have here translational boundary in the San Andreas Fault. And what we're going to look at today is we're going to look at complications with strike slip or translational boundaries, and we're going to focus in on our own backyard in California. I left that other institution on the East Coast because it's on a sand spit. And I'm a geologist. California has the greatest geology you're going to see in any state. It has all types of deformation. It has all types of boundaries. It has the convergent boundaries north of the triple junction here at Cape Mendocino. It has strike slip. It has pull apart basins. It has all of these types of tectonic deformation that I introduced. And so it's a perfect place to come study how tectonics leaves a signature or fingerprint on the morphology. And let's just briefly look at that. This is the Mojave Desert, the Garlock Fault, okay, the San Andreas. These features have a prominent manifestation in the morphology. You can see them. Although I'll tell you, when you drive here and you go up 395 and you're driving up into the Owens Valley, which is here, Panamint Valley, Death Valley, once you get closer to this fault, it looks like you could go up and put your finger right on it. But when you get closer to these faults, it's very hard to find exactly where the fault is. A lot of times, faults are easier to see far away. And the closer you get, the more complicated it gets. But here, this here is a big four-arc basin, the Great Valley. This is the #3 largest producer of oil in the United States, behind the North Slope in Alaska and the Gulf of Mexico, something that surprises a lot of people. The Sierra Nevadas, with some of the highest mountains in the Sierra Nevadas, Mount Whitney, sitting here right on the western scarp of Owens Valley that's been reactivated by normal faulting. Okay, so what we're going to do is we're going to start focusing down into this area here, down into where we live, and kind of just keep circling down into La Jolla. But California, we've done studies in Lake Tahoe that I presented last time, and the tectonic deformation and some of the understanding that we've developed from California, I think, has really given us good insights into this interplay between tectonics and morphology. So what are some of the things we're studying? Why are we motivated to go out and study this area? One of the big things is here, if you look at the Rose Canyon Fault coming offshore here and stepping across, how does this fault match up, or a continuation of the Newport Englewood Fault? So we've been mapping just this last summer up to Dana Point, down to here in La Jolla, and we're going to then move further north, and we're going to map this section this winter, and we're trying to connect up and understand the complexities along this fault system, and is it interconnected, or is it a series of splays that are offset? Okay, so now today we're going to focus in on the Rose Canyon, and we're going to look at some of the interactions of this translational boundary, which is a right lateral fault, and we'll talk about that. But here, what we're doing is we're moving this plate to the north with respect to the North American plate, okay? And so here, these are right lateral faults, just like the Elsinore, San Jacinto, and the San Andreas Fault, all distributing some of the strain across this area associated with centimeters per year motion of the Pacific plate with the North American plate. So we'll look here at some of the complexities that arise, and that the plates don't just simply slide by one another. How are we able to do this? Out on this cruise, Nigella mentioned we brought a lot of the associates of the Birch Aquarium out to sea with us on Friday on our 100th centennial. And as we were out there mapping these faults, a gentleman said, well, why is it taking you 100 years to do this? Okay? And I think the real answer is that technology has made advances, and we're starting to incorporate new technologies that allow us to see the Earth on a scale of the processes that shape it. Okay? So it's technology breakthroughs that are allowing us to do better in this harsh environment. We know more about the surface of Mars and Venus than we do about the bottom of the ocean. And it should be our charge that this resource out here, before we start altering it or putting too much pressure on it, it'd be nice to better understand it. And it'd be better to acquire more data. And the bottom of the box is the seafloor. And the ocean there, we need to understand the seafloor and how this interacts with habitats and things like this, so that we know this resource before we put too much pressure, and we can maybe mitigate some of the problems. I don't think we can hope for much more than that. Our group here in the Scripps seafloor mapping technology is that we have swath data. And this swath data allows us to look at the morphology of the seafloor, the seascapes. So it gives us very detailed pictures of the underlying seafloor, okay? And we can generate swaths as we drive the ship back and forth like mowing the lawn. We also have side scan data, and this side scan data, what it does is it tells us a lot about the roughness of the seafloor. So when we combine side scans, shown here, with bathymetry, we get an idea of the relief of the seafloor and the roughness, so that we create images that tells us something about the surface of the seafloor or the seascape, the morphology. We've developed a new seismic source. This seismic source generates energy. If you hear it, it sounds like a 300-pound cricket when it goes off on the deck of the ship. And it generates energy, and this energy penetrates the seafloor and was reflected back to the surface off of interfaces that have different properties, specifically density and velocity changes, so that we're able to look at what used to be the morphology that's now buried. Okay, and it's now stratigraphy. So these sediment layers and their patterns, we can read, we can sample them, and we can understand something about past history of the Earth. This is the new instrument that we've developed here at Scripps. These other instruments are being evolved, but the ones we're employing are commercially available. Just to show you, this is some of the data. This shows our instrument at the top. Okay, the seismic data, and I'll explain a little. This is off-the-shelf and an off-the-shelf system. And here's the system here with a side scan, this torpedo-like instrument sitting above it. So this one, the chirp, looks directly beneath us, and it gives us pictures that look like road cuts. Okay, so this would be like if you were driving by a road cut and could see the stratigraphy. So this is depth, and that there is roughly about 10 meters. And you're looking at a scale of about 200 meters here. And you can see the layers. You can see these channels and these features and some of the layering. This is an artifact of this chirp system that's off the shelf. And here in the channel, you can kind of see the channel here. These are all over the same piece of real estate. We had a bake-off. The companies weren't very happy that we did this, but and I won't say who they are. But you can see, and in this one, you can hardly see the channel at all. Okay, so these are two different off-the-shelf high-resolution instruments, and we're getting to see a lot more. And we had problems with our data boards here, and we had data drop out, and in fact our fish died right about here. So I'm not showing the best data that we've ever collected, but it's coincident with other data, and it's this instrument that's allowing us to look beneath the surface and see some of these features that we haven't been able to in the past. So let's here jump to La Jolla. The Rose Canyon Fault comes out right here, and goes offshore, comes into this arm of the Rose Canyon. In fact, you can see closely where the fault is right on the beach, where you have the dark Cretaceous mudstones exposed versus the reworked sands that are eroding from the cliffs and being supplied by the rivers in this littoral cell that has a predominantly southward transport. So the fault is coming right out by the beach and tennis club here. And here is a picture of it coming like this, and this right lateral fault takes a left lateral step. Mount Soledad is going up. This fault has millimeters per year motion on it, translation, and Mount Soledad is going up because of this left lateral jog. And I have an image later that I'll show you why this works. But it's a space problem. When a right lateral fault has a left lateral jog, there's compression. And one side of the fault has to go up. And this is controlled by the dip of the fault. So here, Mount Soledad's going up and exposing these mudstones. The kelp beds are predominantly here where the Cretaceous mudstones are exposed. So this is a geologic control on a biological habitat. And I'm going to show you another example of this that we've discovered further to the north. Okay. The fault here seems to control the southern arm coming out the Rose Canyon that joins with the Scripps Canyon that also appears to be fault controlled. And these canyons, the confluence then joins to be the La Jolla Canyon offshore. This is just another rendition. This is from Pat Abbott, Tom Rockwell, Pat Abbott. I've done some great work onshore. And our work offshore complements and helps us together understand this onshore-offshore system. So here you can see the Rose Canyon fault. Mount Soledad's going up because there's a left lateral jog in the fault. This plate is moving to the north with respect to this plate. So here, when it takes a left lateral jog, there's a space problem. Okay, so here, if you owned a house on a right lateral fault like this, right lateral fault being here, we get displacement on the fault, so that if you're standing on this side of the fault, your house is moved to the right on the other side of the fault. Conversely, if you're standing on this side of the fault, your porch is moved to the right. So this is a right lateral fault. And what happens with a right lateral fault, which is like the Rose Canyon fault, is that if you put these jogs in it, okay, you can see that if this plate is moving to the north, with respect to this plate, that in this area you get compression. You have a space problem, okay? Well, what dictates which side of this plate goes up? If the fault is dipping to the south, then this plate goes up. If the fault's dipping to the north, then this plate goes up. So here's Mount Soledad. The fault's dipping at about 85 degrees to the south, so Mount Soledad is going up, okay? Later in this talk, I'm going to show you data offshore where the fault takes a right lateral jog. What's important here is now I have a space problem in the opposite sense. So here we have extension here and we start thinning the crust and making subsidence or a depression. So here the thing to take away is if I have a right lateral fault with a left lateral jog, I get compression and uplift. If I have a right lateral fault with a right lateral jog, I get extension or subsidence. Okay? All right, so this is about the point where we showed some data in the last talk. So from here on out, the review period's over. We're now going into new stuff. Okay, so in fact, we added the bathymetry. So I ended last time showing this rendition. This is the topography of La Jolla with this aerial photograph draped over a digital elevation model with the offshore. Okay, so here's the Rose Canyon, the Scripps Canyon bifurcating going into Black's Beach. Great surfing spot there. The fault curls out and goes out here. I want you to notice this little indentation. Look at the shoreline. The shoreline again steps out abruptly here. And we'll come back and talk about this a little later in the talk. Okay? So here, what we're noticing, Mount Soledad's up high, the fault curls around it. Ardath, or La Jolla Parkway, exploits the fault coming down into Scripps, okay? And so here, Mount Soledad is popping up with respect to the other areas. So the fault curls like this and goes out here. Okay, so now This again is from Pat Abbott, just showing some of the formations and the mudstones of the Cretaceous that are being exposed in La Jolla Cove and are really important for anchoring the kelp beds. We don't see much of the kelp beds further north where there's more mobile sands. Okay, now we're starting with the new stuff. I'd like to also acknowledge the mapping group up at Mbari and Pat Amimpeto. He's provided some data that's gone into this. We're going to start focusing here, looking at this feature here, and also some of the work we've been doing near shore of imaging the thickness of the sands. This is some of the near-shore bathymetry that we collected with a submetric system. We deployed our gear off the pier on a crane, climbed down the ladder, sat on floating rafts, and attached it to the small ship, the Sycon, and were able to pull it off. So each day we'd deploy the equipment off the pier, climb down the ladder, throw all the power cables onto the ship, tie it up, and steam off and collect data. At the end of the day, we'd climb up the ladder and pull all the gear and store it on the pier. So I got in good shape for a while, and now I'm back to where I started. This data goes into about 2 meters water depth. We're processing this data. The submetrics is designed for shallow water. It gives us about 15 times water depth swath. The swath systems on our large ships only give 3 to 4 times water depth. So when you get in shallow water and you're in like 5 meters, your swath width's only 15 meters. So it takes a huge time to map or mow the lawn. So you want to maximize the swath width because then you minimize the time mowing the lawn. So this instrument allows us to rapidly collect the data and fill in the near shore. This here is from Doug Inman, Pat Masters. We have a new student that's working with us trying to understand some of the sand transport. Doug Inman's been doing this for a number of years and has contributed to our understanding of this littoral cell that goes from Dana Point to La Jolla here. And what you'll notice is that 2 of the largest drainage systems, Doug has pointed out numerous times that these drainage systems, the Santa Margarita and the San Luis Rey, that this is probably accounting for a majority of the sediment coming in this littoral cell, and where they enter into the system is very near one another, okay? So this is an important sediment source. The sediment transport from Doug's work is predominantly to the south in this littoral cell, and then we enter into the Mission Bay littoral cell as we go south. So this is the end of the littoral cell. The sediment doesn't seem to make it around the point. Okay. What we're trying to understand is how the modern day processes that Doug's been studying, how can we use that to understand the sediment sequences we see longer term in this area. One thing I need to tell you so that you have a reference framework of what I'm going to show you is that sea level, the Holocene here is the last 10,000 years. Okay? So we're going to be talking 10,000 years. When I talk to people about 10,000 years, people think that's a long time. When you talk to geologists, they go, oh, you're studying the last tick on the clock. Okay, so it's all relative. All right, so this is very high resolution studies to a geologist. 10,000 years sounds pretty long to us. So here, about 18,000 years ago to 21,000 years ago was the last glacial maximum. A lot of the water in the ocean had been sequestered on land as large ice sheets. About 125 meters is our best estimate of how much sea level had dropped in response to storing it as ice on land. As the sea level rose, it did it in fits and starts with pauses that were slow. Okay, so as sea level rose back to the present, it wasn't uniform, it wasn't linear. Now imagine sea level rises very fast. I can cover landscapes and not erode them. Sea level rises slower. I expose it longer to wave-based energy and erosion. We call it the wave-based razor. There's nothing more efficient than waves at eroding topography and landscapes. If you're a homeowner and you're on the sea cliff, you understand this quite quickly as it starts to erode into the sea cliff. It is an incredible erosive agent. So here, what I'd like you to focus on is that the rate of sea level rise from about 8,000 years to present has slowed. This slowing has exposed the nearshore area to a long duration of wave energy and peniplanation. We call this the transgressive surface. So as the ocean transgresses or moves across the land, the waves can eat at the landscapes, they erode it, they erode the highs, and they put the sediment in the lows. So it makes a very flat feature. Okay? And you'll see this in a number of profiles, and I want to call your attention to this because this is the benchmark that we're going to use to allow us to look at the Holocene or modern sands. This is some of the seismic data that we collected from the Cove up to Penasquitos Lagoon, and I'm going to start showing you some of these seismic lines that are parallel to the coastline first. Okay, so here, this is the Scripps Canyon. The vertical exaggeration on this, these light lines here, that's 7.5 meters. This distance here is 200 meters. Okay, so we have about a 20-to-1 vertical exaggeration. Okay, so the vertical scale is much less than the horizontal scale. Okay, what you'll notice is this is the surface here that was cut when sea level rose across the landscape. And you can see these layers come up and they're truncated. This here is the seafloor. Okay? Now look at this wedge of sediment. All right, so we're looking from Scripps Canyon. I've hung this off of Scripps Canyon northward. So we're looking up towards Penasquitos Lagoon, Bathtub Rock in here, back down towards the Scripps Canyon, the northern fork. Look at the thickness here. We're talking about 20-25 meters of Holocene sands, or sands that were deposited since the sea level rose across this landscape and truncated and eroded the underlying morphology. Okay? We're here in about 20 meters water depth. All right, and you can notice this and you can pick this out. These other reflectors, this is what are called ghosts or multiples in seismics, and you can see that it just repeats. This is a mirror image of this, and it bounces off the sea surface and we see it again. So you'd be remiss to interpret this as real. This is the real part of the chirp data I'd like you to focus in on. Moving further offshore, we see that this surface is not always peneplain, that it has relief on it. This is this transgressive surface that records sea level marching up across this surface, coming towards us. So again, from the Scripps Canyon to the north. So this is a long strike, and there's a lot of variability in the relief of this surface along strike. I'd also like to call your attention to these features here. Look at how laminated they are, and they onlap or pinch out against this relief. What we've noticed, and I'm going to show you a series of profiles, what we've noticed is the Holocene sands have very little changes in their character. They're transparent. So that means they don't have much change in their density or velocity that would give rise to a reflector. So the Holocene sands above this transgressive surface are very homogeneous. We might interpret that the wave energy is winnowing out the fines and sorting these sands and removing the fines offshore. Okay, so the sands are very uniform, they don't have differences. As you look here, there's these laminated packages, and I'll show you, they only occur near the Scripps Canyon. And what we think is that the canyon plays an important role during the sea level rise. The story goes something like this. Here I have a depression or a canyon. As sea level starts to rise, what happens is this canyon acts as an inlet. It allows the water to flood in behind and fill lowlands in the behind area. So you have barrier beaches offshore that are seaward of this area, and this would be like a lagoon. And the reason we think it's laminated here is that you've got muddier sediments, they're protected from the high energy reworking, so you get lamination. And these laminations we think record a lagoon developing behind the inlet, where seaward you have a barrier beach. And I'll show you a few more lines to this that attest to this. So now what I'm going to do is now that we're kind of all experienced in looking at these records, I'm going to hang all of these profiles off of the Scripps Canyon. That's to help register you, and we're going to look to the north, this being near shore, running parallel to the coastline, and systematically moving offshore. This is the line that I showed you with much more vertical or exaggeration. I think it was this one here, and I showed you this line offshore. I'm going to show you some blow-ups to highlight some things. The Holocene sands pinch out near Bathtub Rock. We believe this is the Del Mar Formation. It's an estuarine formation. It's lithified. It's shelly. It has articulated shells in it. And it grades into a sand as the barrier beach migrated across the estuarine region. But this is the Holocene sands. So their thickness along the strike of the margin is not uniform. It varies and thins to the north. Okay? So this is something that we didn't know when we started because it's not demonstrated in the bathymetry. You would not predict this by looking at the surface of the seafloor itself. So here, how much of these sands are mobile? How much are available to be reworked, be brought back to the beach in fair weather conditions? We need to understand this because this is our sediment supply that's actually recording input after the last sea level rise. Another thing that we found interesting is across the Scripps Canyon, here's the transgressive surface here. Many times the thickest sediment after the sea level rise was to the south of Scripps Canyon, and in fact the thickest sediment that we found in this littoral cell was right out in front of Scripps. It's in between the two canyon heads. So if sediment transport is running from north to south, how do we get it across this canyon? Was the canyon maybe filled or during the low stand and wasn't an efficient trap? Was sediment moving around the head of the canyon? These are things we need to investigate. What are the sources of the sands? We have an interplay of the cliff erosion versus river input. And there's a debate of which one is dominant and which one is subordinate. Does it change through time? We don't know. Okay? But that was something that we hadn't expected. Here's these deposits again, these flat-lying deposits that onlap, and you can see them in these bottom three lines. If I back up, you can see them here, you can see them here, and you can see them here. So they're on the outer part of the shelf where we believe that flooding through the canyon infilled this low. See the topography on this feature? There's about 30 meters of relief. And the estuarine area came in and filled to the same datum on each of these profiles, which is consistent with it being an estuary or flooding in behind the barrier beach. This is now a dip line. So the other lines we call strike lines. They run parallel to the shoreline. Now we're running from shallow water, across the canyon head, out to deeper water. You can see this transparent area here. You can see the roughness on this transgressive surface, and here's the onlapping packages I talked to you about that have more reflectivity that we think might be estuarine. And we'll be out sampling this in next summer with a deep vibra core to try to sample these and test our predictions based on the seismic data. Okay, so now we're interested in this because here I'm looking at timescales that are thousands of years. Researchers here at Scripps are looking at timescales that are years, monthly, daily of the wave activity, the sediment transport. How can we jump scales to understand what are we looking at today that makes it into the geologic record, and how are these processes integrated over longer timescales? Okay, that's what I'm interested in, trying to understand sediment budgets. Where did the sand come from? So can we establish sediment budgets above the transgressive surface and look at its thickness and distribution and understand whether the river sources have played a dominant role, or is it cliff erosion, or is it some combination of the two? So here, as we look at this area here, I told you that we're going to look at an area where we see subsidence, or what we think is a right lateral step. Okay, so here is another area offshore that's shallow, the contours take a rapid jog to the west, and we have this platform sitting up here. The fault enters here and exits here. So again, this is another left lateral jog, and would tell you that this area is undergoing uplift, and this is very analogous to what's happening at Mount Soledad, except for the dip of the fault might be dipping to the north this time, and this area is popping up, and it's causing the isobaths, or the contours, to step out seaward and give us this broad plateau. Within this plateau, however, there's complexities that I'm going to show you, and basins developed. There's a lot of theory in tectonics about what happens when there's a right lateral jog with right lateral faults, or a left lateral jog with left lateral faults, something that makes extension. Here, this is from Deep Springs Fault, which is just east of Owens Valley. So here we have a right lateral fault. Plate A is moving to the north with respect to plate B. One model would say that the intervening area between these plates, where we have this space problem, where we make space, starts to rotate like books on a shelf. Okay? So here you can imagine that you'd get a very complex stratigraphy. In some places you'd get compression, other places you'd get extension, and it would depend on how the books interacted with the fault zone. So it would create a very complex three-dimensional network of basins and compression in this area. Another idea is that this would be plate A moving to the north, plate B moving to the south, that you get faults that are orthogonal to these main bounding faults, and that you actually move the block out like this and create a basin with a dominant structure at a high, at a high angle to the strike-slip faults. This is hotly debated in structural geology and tectonics. And here we have a place in our backyard that can illuminate some of these problems and structural styles and how plates deform. Okay, let me just locate you here. So you're looking back up into the Rose Canyon. Here's where the fault bites into this plateau. Here's this plateau stepping out. What I'd like to call your attention to is this scarp that runs like this, and this other scarp that runs like this, and you can see it here in the bathymetry. And I've shaded the bathymetry to highlight these scarps. Now we've collected seismics across this, and it looks like this. All right, so here, what we're looking at is we're looking at an area where the fault comes in, steps over to the right, and here, this is depth, we're looking, this is 10 meters here, subsurface, 200 meters here. This is going shallow up to the shoreline, offshore. What we're looking at is we're looking at this basin forming. This is this transgressive surface I've referred to you before. You can see truncation beneath it. In fact, the Holocene sands pinch out against this hard ground that's exposed here, and then you can see them reappear here and thicken in this area, and then they abruptly terminate against here where we infer there's this fault. Likewise here. Look at the divergence of the packages. We're seeing 40 meters sub-bottom with this chirp system. In sands, this is really incredible. So why is this important? Why am I excited about finding this basin? So we found this on a student cruise funded by UCSD and Scripps. Before the budget crisis, we used to have ship time allocated to bring our students out and teach them oceanography. And hopefully, those days will come back and the economy will rebound, and we'll again be able to train our students more at sea on these cruises that are funded by the state. So the reason I'm excited by this is that this here, and this is the next seismic line, you can see the fault here. Here's the transgressive surface here. You can see the change in the lithology and the rolling over. This is an artifact, this is a ghost, and here's your multiple. These basins, where we have subsidence and sediment accumulation, is going to allow us to date the activity on the fault. You can imagine that if I have two plates moving by one another, it's very hard to date the fault. In fact, it's very hard to know how much it's moved, because you need piercing points that go through the fault that allow you to know that. So even understanding the horizontal displacement on strike-slip faults is difficult. but understanding their age is even more problematic. So when we can go and find areas where there's been subsidence and sediment accumulation, we can put constraints on how old the fault is. How many times did it move? What might be its recurrence interval? So this is important if we ever want to understand what is the likelihood of another fault in the next 100 years, 1,000 years. We're never going to be able to predict when faults will actually happen, but we might get a better understanding of their probability in time frames by looking at their occurrences in the past. So here, again, is another crossing going from shallow water, depth here. So here, looking at this thickness of the Holocene, and you see that offshore, it pinches out, and here's exposure of hard grounds here. Okay, so here's the fault, and the fault on this side is not so well displayed, but I'd put the fault possibly over here. Let's look at the next line. Here, you can see the fault quite nicely. You can actually see this couplet. These two reflectors are these two reflectors. So we've actually deformed and rolled over the layers, faulted them here and here. So this is a little basin. We're talking here, this is about 200 meters, and this here is about 7.5 meters. So keep in mind, these are highly vertically exaggerated, but this shows for the first time some of these features offshore that we weren't able to image in the past. And they're tape recorders of how this fault moved and when maybe the first time it moved. So we could actually look at the sediment that accumulates above this couplet and try to understand by dating techniques how it happened. See these things here in the water column? What we've noticed from many crossings of this feature and we can see fish in this instrument. This instrument's recording about 500 hertz to 16 kilohertz. We also had side scan data out there. And whenever we got near this hard ground, where the underlying material that's harder was exposed at the seafloor, we started to see more fish. Okay? Interesting. So now here's another place that's similar to Mount Soledad, where we have outcropping of hard grounds, and maybe this is another habitat for an ecosystem that we hadn't had great constraints on. So when we were going out on the Centennial cruise, I didn't tell the associates that I thought this because I was afraid we'd had like 3 cruises, we'd seen fish. I'm there, what happened? They're not there today. So I didn't want to put the camera down and not see any fish after I told them there'd be fish all over the place. Okay, here, look at this. This is the transgressive surface again. Again, 7 meters, roughly about 200 meters. Here's the Holocene sediments. Okay, these sediments are probably about 8,000 years to present. Okay, so we've got about maybe 7 meters here, and the last. So you're talking about a meter per 1,000 years. Okay. So here, what we're looking at is there's a fault scarp here, and we wanted to go look at this fault scarp with a camera and try to see if we could see a habitat control and what was the nature of these rocks that are exposed on the seafloor here versus the sediments. Yes, we still work with Hui. So we brought scientists out in the Centennial cruise from Woods Hole with TowCam, Dan Fernari, who he got his training here at Scripps and is making Hui famous. And so here, he went out and we took pictures. This is a CTD and a bottom camera system. We only had a couple of hours, so we didn't get to see the fault scarp. We only were seeing the Holocene sands, and this is what it looks like. This picture is about 4 meters across by about 4 meters in depth, and you're seeing the sandy substrate of some of the Holocene sediments, probably some silt component, a few fish here, but we didn't have much time for the camera tow. So we're going to go back. So any of you are welcome to come with us. I'm going to try to put together everything I've told you in this 3D rendition. We have this rendition available. It has linked in it bottom photographs here of the kelp bed, Scripps banner here in the background. Now we're looking up the La Jolla Canyon, up into the Rose Canyon, the Scripps Canyon branch, over here, over into the kelp forest. Now I've linked all these profiles along the canyon, so you can actually see bottom photos of sponges and other data that's been collected. We've linked in all the networks, so how do we understand the subsurface? So you can fly like a fish through this data volume, you can fly like a mole. We're going to go over here and look at the fault over here on this area where the contours step out dramatically to the west. After this, I have a quick run on what the tsunami predictions are from our model, so if you give me 2 more minutes after this, I'll run through and tell you the results from what we started last year and I warned you about. So here, there's freeware to run this on your Mac or PC. I have this scene. You're all welcome to have it. We can burn it on a disk. You can go home and you can fly through it yourself. Okay? So this data volume is available to anyone. It's great for outreach. It allows us to take a lot of data and digest it. Okay? So visualization is very important for how we integrate all of this material. Okay, let's jump back. I showed this picture during my talk last year. The warm colors are shallow, the cool colors are deep. This is a survey I did on the Atlantis. We did some Alvin dives down here to look at some of the overbank deposits and trying to see if there was a climate signal in some of these. What you'll notice is it looks very much like a fluvial channel that you'd see on land. It has meanders, it has cut banks, point bars. What I'd like to draw your attention to is this is a different rendition now. We're looking offshore of the Scripps Canyon. Look at these terraces. What we thought when we first saw this, that these might be when the channel was younger, it was wider, and it's narrowed down through time. Another depiction just showing you these terraces. So the model went something like this, that it could be that it just was the channel narrowing down through time, or it could be these blocks. I told you if it was scenario A that we wouldn't go much further. So you know that scenario B probably won out. We have seismic data that shows that these blocks are fault controlled and down dropped. We have some chirp data off this that we're going to process, but these blocks in the canyon are faulted and have clear fault boundaries, so they're down dropped. So we asked the question, what would happen if these failed? So we took a conservative estimate. The terrace probably goes up further. We took a conservative estimate mapping out the size of these blocks, and we asked the question. Here shows the cross-section of the blocks, and you can actually see they back dip in morphology. They appear to be fault controlled. What would happen if these blocks tumbled down and fell into the canyon? We used a simple wave-based model. In this model, we used a number of pistons, the blue pistons. They can all move vertically or horizontally, or a combination of the two. But to simulate the mass moving through this failure area, we had the blue pistons move down and the red pistons move up. Okay, so here, this would be the slide motion to the north into the canyon of those blocks. And here is our first modeling results of what size tsunami. So here's the failure. These points here. This point here corresponds to here. This point is right out inside of the director's office, which is right here. So in 4 minutes, a tsunami would pretty much be on top of the Scripps director's office. This shows the 8-minute. Tsunamis travel about 400 to 500 miles an hour in deep water. They travel about 60 to 80 miles an hour in shallow water, and it depends on a lot of the frictional forces. So here, let's just look what the director might observe one day after this happens. So here he's sitting kind of pondering the future of Scripps, and he sees a large wave come in that's probably about 1 meter, and the surfers are doing a great job. Then they're all grounded, and none of the surfers can get back out. Okay? Followed by that is a 6.5 or a 6.4 meter tsunami wave that would come in at about 80 miles an hour. Okay, so here, what does that mean? So here, if we look at Scripps, what we've done is we've put on the 6-meter elevation here. Okay, in the summer months, about 17,000 people a day visit the La Jolla Shores Beach. If you recognize any of these streets and you're a homeowner, we'll put you on the phoning list. Property values, I would say I didn't see many houses in this area that were at this price, but this is what the UC professor and sociologist gave us as estimates. I don't see that till you get to Canada. So, anyhow, so what we're seeing is that if these blocks fail, we have very short time to respond, and this area, a wave about 6 meters will crash on us about 80 miles an hour. So it's something to think about. These canyons are also, they're inlets during sea level rises. They provide estuarine areas. They're probably areas where archaeology would be focused. They're also areas of hazard. Another thing that you can take away today is we're trying to understand the sediment budget. Where does the sediment come from on longer time scales? And how can we integrate some of the great work that's been done on short time scales to understand this Holocene sediment thickness? And with that, I'll leave you where I kind of left you last time. We're teasing out some answers. We're raising more questions. It's a fascinating area here in La Jolla, and thank you for your time.